But that's a bad sign because maybe I don't know so much. But on the other hand, while I was preparing for this talk, it seemed like a good sign because there were some mysteries that came up. So maybe you know, the mysteries will you know, you guys have another few weeks in the semester to sort things out, right? So I'm only here for the week, but call me if it works out. Okay, so this is an aspect of matroid theory with a topic that, you know, you could probably pick it up earlier, but the real thrust seems to begin in about the mid-2000s with the thesis of David Speyer, the thesis of Fink. And I was going to actually sneak in here earlier and write down about 10 references because there are a lot of references, but I didn't make it early enough, so I'll just have to bluff it a little bit. If I don't mention your favorite paper, especially if you wrote it, please don't be offended. Okay, so then maybe in some rough historical development, I'll say what the construction is, and then end up with some recent results of Chris Eur, Eur-Huh, and Eur-Larson, who have a result which maybe makes a good end to the talk. So let's see. So do we define a matroid? Probably not. No. Okay. So so my ground set, I want to call it E, but it's really the numbers from 1 to n. So let's take the matroids of rank R particularly and think about the matroid polytope. Now this goes back to the 1970s. I take the convex hull of the indicator vectors on the bases. In this n-dimensional space. But then we know that bases all have the same size. So this is really contained in an affine hyperplane where all the coordinates add up to whatever they add up to. I guess it's R is the rank. So your matroid polytope is given to you as a convex hull. But you can also write it as a polyhedron by giving some linear equations. So those would be given by taking all subsets of the ground set and asking that the coordinate sum is bounded by the rank in the matroid of that subset. And it turns out that you don't need all the 2 to the n subsets, but it's enough to take the irreducible flats. So a subset's a flat if it's maximal with respect to rank, and it's irreducible if the matroid you get by restricting to that flat has only one connected component. So this, it's almost a cliche. I know some people smile, or I do, when at this part of the talk, now we draw the octahedron, right? I'm going to talk about valuativity, the matroid U24, has 6 bases. Instead of writing the indicator vector, I'll just write the bases. And then the question that comes up in history is the question of dissecting matroid polytopes into little matroid polytopes. So there's the search phrase for the Google search, matroid polytope decomposition. I think there may be some reason to do this in classical matroid optimization problems going way back, but I don't know what it is. So I'm going to say that the first thing I know about why you would want to do this is if you had evaluated matroid, then the underlying matroid has a matroid polytope, but the valuation gives numbers on the bases, and it induces matroid polytope subdivision. And so if we look back at Speyer's tropical linear spaces, then actually, if you've been to a talk by Derksen-Fink lately, you might have heard about this too. So let's say there's a good reason to do this, but also, just kind of naively, you want to learn something about matroids. Perhaps inductively, we can work with smaller matroids. And so for this one, of course, you can see it as a union of the upper and lower matroid polytopes, where if I do the job right, the associated matroids are ranked 2, where 3 and 4 are parallel and 1 and 2 are not down here. You see, whoops, didn't do it right. And then the roll of 3 and 4 and 1 and 2 are exchanged as I flip from the top to the bottom. And then on that middle slice, that's the intersection of those 2 matroid polytopes is also a matroid polytope for an even more degenerate matroid. So let's see. So let's remember maybe that if I have 2 matroids on the same ground set, and the matroid polytope for the one sits inside the other, then the matroid with the smaller polytope is a weak image of this one. So weak map is simply a let us assume that the ground sets are the same, simply a pair of matroids where every independent set in this target matroid was independent in the source matroid. So informally, it's just like more degenerate. And so I guess if you make your polytope smaller, that's what more degenerate means, convex geometrically. So that's somehow, this polytopal dissection comes with weak maps that form some diagram that goes with it. But it turns out that this is a little bit rigid, since some matroid polytopes don't admit any non-trivial decompositions. So So if I were interested in, inclusion-exclusion properties for matroid polytopes, it might be wise to allow a slightly, broader set of operations. So for that, let's say, let's take the indicator function for a polytope and denote it by this. I guess any convex set, or actually any set, has an indicator function. But I'll only be interested in convex polytopes. And then we can consider what happens if I took a matroid to the indicator function on its matroid polytope. I guess that lives in the space of functions. R to the E to R. So if you know McMullen's polytope algebra, for example, or convex geometry likes to consider things like this. I guess I can. This is a vector space, so I can at least take the abelian group on the matroids. And so now I'm sending a basis vector to an indicator function and extending linearly. Could do that. So let's let the group of valuations of rank R, the group of matroids, what's that called? Matroids modulo valuative equivalence, matroids of rank R, be the largest thing that makes this diagram commute. More precisely, if I consider this map and then take the quotient by the kernel, that'll be what I call val R. So if you look at these polytopal dissections, if you digest this, the indicator functions behave well on the dissection, and some inclusion-exclusion relation is satisfied, so that my inclusion-exclusion relations are definitely in the kernel of this map. But it's a result of Derksen and Fink that those generate the kernel. So I won't make a precise statement, but if you're interested in studying the polytope decompositions, then you're free to use this. It looks like I might have taken a quotient by more things, because when I add and subtract these indicator functions, it could be that more things go to zero, but then the theorem is that they don't. So this is really good. So let's have a matroid invariant. So now you could ask, do I mean like a matroid invariant that's constant on isomorphism classes? Or well, that's a subtlety. Let's just say a matroid invariant is something that sends a matroid to an element of an abelian group. And we'll say if if I linearize mu to make it a map from here to the abelian group, that it's possible that it actually is well defined on this. And if so, that's a valuative invariant. So these are invariants that would, somehow vanish on deletion or on inclusion-exclusion pictures like that. So let's discover a valuative invariant. Dave, can you can you tell me some property of a polyhedron that would give you something I would assign to a matroid polytope that would be valuative? Sorry to put it on the spot. Yeah, you probably already know the answer, but maybe, or any answer. But...
How about Speyer's Jr.?
Yeah, right. Yeah. So, I mean, maybe the cheapest one that isn't like the Euler characteristic is to say, maybe count the number of vertices, because a matroid polytope, the only integer points in it are the vertices. So then the number of bases is such a thing, because it's going to satisfy inclusion-exclusion. And it's enough to check under matroid polytope subdivisions. But yeah, so then, yeah, I guess, you could take the volume, but that's like for any polytope, that's a valuative invariant. But then Dave says, well, I count lattice points. So the way you do that around here is to look at the Ehrhart polynomial, right? So a little more sophisticated, but it's not because counting lattice points satisfies inclusion-exclusion. This one's clearly valuative as well. So those are obviously valuative, but then the miraculous thing is that it became clear in over the course of some years that
example, taxpayers paid $49,000.
So they did. So these were obviously valuable, but then the point is that, and this is where I could mention papers of Ardila, Fink, Rincon, Derksen, let's see, more papers to mention. But we start finding that certain invariants are valuative, but they're not obviously valuative. And then there's let's see. I guess the one that I find the most surprising is the type polynomial of a matroid. So I'm going to assume you guys have heard of this, but if I send m to the type polynomial, which is some generating function for matroid basis activities, so some kind of refinement of this is still a valuative invariant, which is kind of shocking maybe because the way you define it in matroid school is usually by say deletion contraction, which gives you some recurrence, which allows you to build this up. And so this is saying that there's some kind of rather orthogonal recurrence that builds it up as well. So So you might see a recent paper of Luis Ferroni and Benjamin Schröter on valuative invariants. So the Hashtag-Lustig polynomial of a matroid. The matroid volume polynomial, Chris Burr showed was valuative, etc. I guess the stop me if I'm wrong, but I think the Chow polynomial of a matroid is not a valuative invariant. If you need an example, it's not an example. And then true, yeah, that's not it. Good. Oh yeah, so if the type polynomial is valuative, so is the characteristic polynomial of the matroid. And maybe in a paper of Jose Bastidas or somebody else, we learned that if you take the characteristic polynomial of the geometric lattice turned upside down, you get some rather different polynomial that counts something else. And I think that's not a valuative invariant. But that's a little bit obscure. Arguably, that's not too obscure. But this notion covers a big swath of good time I asked for any questions. Yeah.
Does the name have anything to do with some sort of valuation or no?
Yeah, the functions on the span of the indicator vectors of convex bodies are called valuations for some reason in the theory of Hadwiger and McMullen and etc. And so it's I'm not sure, it doesn't have to do with valuated matroids though, or valuations on a ring that I know of, or not obviously. Yeah, that's yeah.
Is there any precise way in which matrix polytope decompositions and deletion contraction are, like you said, orthogonal? Is there any precise way to say orthogonal?
No, that's not that I know of. Yeah, that's a good question. The one thing that's at work here is that this was a rank preserving decomposition, and then those are mostly rank dropping. So I can zip all these things together. Let's see.
Chow polynomial is valuative.
Oh, it is?
It's 8 to 12 for each.
Okay. Well, that's good. Good news for valuative invariants. So you have to dig a little bit to find something that's not valuative. Oh yeah, right. And then maybe it's a good point too to put you're going to ask yourself, are these valuative invariants universal? Then the answer is oh, not at all. So if I take these two matroids, classically, I guess you know these as the ones that have the same Tut polynomial, but they're not the same matroid. These guys are valuatively equivalent. So any valuative invariant gives you the same answer on that pair. But yet they have the same number of hyperplanes. So it's a little bit subtle what this invariant distinguishes or not.
What are those two? How do I read the matrix out of the?
Oh yeah, pardon me. Yeah, so these are these are points in P2. So these, that's 6 points where 3 of them form a rank 2 flat, and then 3 other ones form a different rank 2 flat. Whereas over here, I've got 2 rank 2 flats that meet at a single point, and then I've got a free extension by one more guy.
The statement is that the sum of their S6 orbit is identical.
Yeah, that is true, because I didn't kill the symmetry, so so any invariant that was constant on isomorphism type and valuative would be the same on those 2 guys. Yeah. So this question about whether you only consider invariants that are invariant under permutations of the ground set. It's best to not do that, it seems, right away, but that's a subtlety in the literature. Okay. Yeah.
So you said that this would give some sort of recurrence for constructing a valuative graph. So do we know the base cases of
Yeah, so it's actually, it doesn't get you where you want to go if you think I should cut matroids down to the indecomposable ones, and then those will be really easy to look at. Oddly enough, that's if a matroid has no non-trivial subdivisions, it's either not realizable or its realization space is discrete. So those are kind of that makes it sound like they're quite interesting matroids. Hardly the kind of base case you want to have. So yeah, so this is a different game than deletion contraction. Maybe you want to build up and to make so let's do that. So let's sorry, one more example in my world here. Something that's not a subdivision, but so if I take this rank 2 matroid, if you guys prefer to think of it as the matroid of a graph, here's the graph. So it's got two 3 cycles joined along an edge. So I could write it as, I could represent it using points in P2. And if I call that M, then M is in the valuative group, I could take the uniform matroid. Let me indicate classes in the valuative group. So this guy satisfies a relation like that. So we don't know that yet, but I guess you can check from your armchair that it's true on vertices, because the bases of this matroid, because it's rank 3, are all the 3 element subsets of 1, 2, 3, 4, 5, except 1, 2, 3, and 1, 4, 5. So here's a matroid whose bases are all the 3 element subsets. Here's one that's missing the 1, 2, 3, and here's one that's missing the 1, 4, 5. So if I add and subtract, at least the vertices come out right. And then it turns out the interiors do too. Yeah, Alex?
There'll be some, these things are all full dimensional. There'll be some relative codimension one. Some atoms that need to go back in there.
Yeah, right. Okay, yes. Okay.
Sorry.
I guess the valuative, co-valuative. So let's see. So we need the notion of cyclic flats. So a cyclic flat is slightly weaker than an irreducible flat, which we had before. It's a union of circuits. These are good guys because, for example, if I look at the dual matroid, the cyclic flats of the dual matroid are the complements of the cyclic flats of the original matroid. And there's a cryptomorphic characterization of matroids by cyclic flats due to Bonham and Dubier, which says basically you can write down any lattice with minor conditions and assign ranks in a way that's, doesn't do anything stupid. And then that determines a matroid. So if the cyclic flats are totally ordered, that would be the simplest possible situation from some point of view. And so such matroids are called nested. I can make the flats initial sequences 1, 2, 3, 1, 2, 3, 4, 5, etc. And just tell you how long the sequences are. These have to go up by at least 2 at each step, but I'm not worried about that. And let Ri be the ranks. So these nested matroids are the Schubert matroids.
Yay.
Finally, yes. Didn't claim the legitimacy there. How many people have not seen Schubert matroids before? Good. You're here. I'm here for you. Absolutely. Okay. So these have a bunch of characterizations, which I'll just sort of point out these are quite beautiful objects because you can describe them in many ways. So I think maybe it's best to illustrate these equivalences with an example. Let's maybe I make sure I pick the same one. So let's make the unique matroid whose cyclic flats are of size 4, 6, and 9 of ranks 2, 3, and 5 when n equals 9. And to tell you how to do that, the nicest way to draw a picture is to say the Schubert matroids are equivalent to lattice path matroids of a certain form. I have to. The nice thing was my notes were on graph paper, so this lattice path picture was real easy there. Probably harder to make it look good. Okay, so let me tell you what I do. So we're interested in the usual lattice paths that go up and to the right, starting from a bottom left corner and ending up at a top right corner. So there's an abundance of colored chalk, so I should probably color the horizontal steps in a less visible color because the upward steps 1, 2, 5, 7, 8 completely determine that shape. And they come from this string by saying that my first inside corner will have height 2, and it'll be 4 steps from the origin. My next inside corner will be height 3, and it will be 6 steps from the origin. And then I'm going to count this as an inside corner too, and it'll be 9 steps in height 5. So we can do that. And so it's a rank 5 matroid, so I can tell you that the bases are the lattice paths, which are the guys who take their up steps, where the first up step is at least 1 and the second one's at least 2, and et cetera. So I'm really looking at ordered 5 tuples, which dominate term-wise this S. So you could characterize these matroids in that fashion as well. And let's see. The matroids are representable via, this is where the Schubert comes in, via generic matrices with the condition that the pivots are in prescribed columns. So if I look at a reduced row echelon form, it looks like this. You can pick out the maximal independent sets of columns by, I think I didn't do it right, did I? Oh, maybe I did. I need to pick a collection of 5 columns. So the first one is at least to the right of 1, and the second one is at least to the right of 2, and ... So as long as my field is big enough so that those stars can all be chosen so that the extra minors which might be around are non-vanishing, I've got a linear realization. Or realization or representation? Shall we vote? Who likes realization better? And representation? Yeah, it's funny. If you ask this to an audience of like structural matroid theorists, the vote splits the other way. So it's almost like having an accent in matroid theory or something. Okay, so realization it is. So realizable. Okay, so Derksen-Fink showed that the nested matroids form an additive basis for this valuative group. So I've got this chain of cyclic flats together with ranks. So that's, oh, by the way, so I guess this valuative group is torsion free over the integers. Now that wasn't obvious either, right? Because I took a free abelian group and I took a quotient by who knows what. So it's torsion free, that's good. And does that follow from this additive basis property, Alex, or was it established some other way?
It followed that wouldn't have known it beforehand.
Yeah, yeah, okay, yeah, so I thought so, yeah. So then these guys are, let's see, right, so I can, uniquely write a matroid as a linear combination of nested matroids. Modulo or, if modulo valuative relations. So if you had a valuative invariant and you could compute it on a nested matroid, which are kind of simple, then this would be a great tool. And so this was the key idea that Ferroni had to show that the Ehrhart polynomial, for example, does not necessarily have non-negative coefficients or not positive in the right range. So you can construct counterexamples using clever choices. If you know some decompositions of some matroids into nested matroids. You can also you can, if you had some property of matroids, which was true for realizable matroids for geometric reasons, and it was the kind of property that went through on valuative relations, then you could extend your property to all matroids. So that's a clever trick, and it takes too much time to say what exactly or where this is well applied, but maybe Eur-Spink and saying tautological classes for matroids sort of make use of that in a nice way. Okay, so that was about additive structure, which came out well. How about multiplicative? Oh, yeah, right. And so at some point I was supposed to say, we did have a example of how to decompose a matroid into nested matroids, modulo valuative equivalence. So you can actually, do some Mobius inversion in the poset of nested matroids in order to make these computations work well. And then the poset under weak order, it's not so bad. If you look at this picture, once again, it's for the Schubert people. So if I consider what a weak map looks like amongst, say, Schubert matroids, it turns out that it's the same as including those partition diagrams. So then the uniform matroid is when I take the full rectangle, and so that's the top of the picture if your weak maps point downward. And so you can somehow control the combinatorics of that poset of nested matroids pretty well. Okay, so how about this? So if you got two matroids on the same ground set, which is still always E, if I take two matroids, I can compute the matroid intersection, which is a matroid by definition whose bases are intersections of bases from the two matroids. So then you say, but if I intersect bases, I may not get sets that are all even of the same size, so it's obviously not a matroid. And so then the the quick rebuttal is that you only take the smallest ones in that set, and those all have the same size, and those do form the bases of a matroid. And so this is the dual notion to matroid union. So this is so let's try to make a multiplicative structure on the valuative group. Sorry for my board work. This is co-rank. Which is size of the ground set minus the rank. So if you look at what the expected size of this intersection of two bases would be, it's geared up so that this co-rank would add up. But that might not be what you get, in which case we better forget it. But if you define a product on the pre-abelian group of matroids using this intersection product with the proviso that you take the graded part, so you throw away intersections which are of the wrong co-rank, then it does induce a ring structure on here. So it's constant on valuative relations. And I don't know if that was known, it must have been known to someone before the next result, but it follows from the last results that this is actually well defined. Maybe Dave Speyer showed this. Implicitly. Let's see. So let's take the permutohedron and its friend, the stellahedron. So I'm going to assume you've seen the permutohedron, which is the convex hull of all the permutations of a n tuple of distinct numbers. And then the stellahedron is in one dimension higher. Obtained by adding in the origin and taking all the coordinate plane projections of the permutohedron. And then that whatever you get, this is the stellahedron. Okay, so they've got fans, normal fans. The permutohedral and stellahedral fans, which allow you to make toric varieties. But if you're running out of time, you could skip that step probably around here and jump straight to the corresponding Chow rings. Of the permutohedral and stellahedral fans. So these are wonderful objects, which they're graded Artinian Gorenstein algebras generated in degree 1. They have Lefschetz properties. All we need today is Poincare duality. I'm supposed to stop after 50 minutes. Am I out of time?
No,
1 hour.
I can take an hour. Okay, yeah, so I'll just relax a little bit.
take however much time you want.
We're getting close to a punchline. So that would be a good spot to stop. So even the Betty numbers of the permutohedral Chow ring are the Eulerian numbers. The Betty numbers of this are known, but I don't remember what they are.
Binomial over
Binomial Eulerian numbers. Yeah. So these are combinatorially significant universal objects. So So you should be happy that I brought them up. And it turns out that, I didn't say what val with the little circle is, but let me do that. But I guess, I allowed matroids with the possibility of loops, but if you look at a matroid polytope, the vertices were bases, right? So you don't really see the loops. They never show up in a vertex. They're just like bonus coordinates that don't do anything. So you could probably have had a variation of everything we said, where you look at matroids without loops. And it turns out for technical reasons, it's better to allow loops and do this, but results of Simon Hampe and Chris Eur, Eur-Huh, and Eur-Larson established isomorphisms between these rings. So this Chow ring is a ring with an intersection product, and his friend, the permutohedral version also. And so these guys have a product given by intersection of matroids. So let's see. I guess it's not just abstractly isomorphic, but isomorphic as graded algebras. The generators over here are matroids, and I can send a matroid to the class of its augmented Bergman fan, or its classical Bergman fan, if you prefer, which is just some subfan of the matroid polytope. In case we could say exactly which one, but it's maybe been mentioned here before that these are familiar objects that pop up. So this is really beautiful. These are isomorphic as rings, where the intersection product over here, given by intersecting matroids, turns out to be the intersection product of Minkowski weights over here, given by intersecting fans using a fan displacement rule. So it really couldn't be better than that. Let's see. So just for example, what you could, this invites you to consider is that since those Chow rings are generated by divisor classes, which you can write down pretty explicitly, this valuative ring must be generated by classes of co-rank 1 matroids. And you can write those down too pretty explicitly. A co-rank 1 matroid is a uniform matroid with one more element than its rank, plus some co-loops. Yeah. And so then those guys, you can actually, let's see, Ferroni and Schröter tell you how to map those over there. And, anything you know about those Chow rings can be brought back to here fully explicitly. Maybe a more important point, though, is that the invariants if you think of an invariant that's valuative on rank R matroids, then in this Chow ring in degree n minus r, there is some class which by Poincare duality is your invariant. That's to say, pairing with that class computes the invariant. So if you think of, someone says polynomial, I say here is a linear combination of nested matroids that is the Tut polynomial. So that somehow says that well, okay, so the dimension of the space of valuative invariants is given by binomial Eulerian numbers. But even the structure of valuative invariants is somehow it's dual to the valuative group. And these things are tied together. So then it leads to the question that we were discussing at lunch. So why on earth are so many matroid invariants valuative? And what actually is really going on here? So the more I think about it, the less I know. So I leave it to you guys. Thanks.
So what are the classes corresponding to some of these famous invariants you mentioned?
Honestly, I don't know. You can work out some sort of easy examples like pairing with the uniform matroids, or maybe the some of all the uniform matroids counts. Sorry, I remember that's a good example. What is the invariant that comes from pairing with the sum of the uniform matroids of fixed rank? But exercise. It's sort of easy, but then more exotic ones. I have no idea. I don't know. It's whether or not it's an interesting question is up in the air. Yeah, Alex.
You know what happens to the Hopf structure on the value of invariance in the Chow point of view?
No. So Alex refers to the chronological weak map for every subset sends M to this sum. And I've got a multiplication that goes the other way. So there's this Hopf monoid structure where Ardila and Sanchez are in the audience, and I don't know that much about it, but yeah. So how does this play on the Chow ring side? Good question.
For instance, the Tut polynomial is just the product of two group-like elements in that Hopf structure. So that's a nice way to find a class representing it.
Yes.
There are like restriction maps where like the boundary of the stellahedron looks like a product of smaller stellahedron and a smaller permutohedron. And that corresponds to that product or appropriately graded version of it. But one of the factors you get loops, like you have to go to the loopless matroid, and it's like a ring map. And if you want to, not go to loopless guys, then it's no longer a ring map. Okay. Yeah, so there's like a map from Chow of sigma E to Chow of underline sigma S times Chow of.
Yeah.
And that's a ring map, and that corresponds to the graded version of this. Only line. Only.
Yeah, right. Yeah. But that follows it up just a little bit, right? So somehow you got to keep these two things together.
So it's not a ring map if
Yeah.
you don't do that. If you don't put the underline.
So to make this,
I always put underlines, it's a ring map, and then this is a module.
if I put underlines on both sides, is it back to being a ring map?
Yeah.
So advertising for the permutohedral story. One thing's a module over the other, so it's somehow, maybe that's not super surprising.
I have a question.
Yeah.
So the stellahedron has a structure that you don't see in the permutohedron, which is that the matroid duality gives an involution of the Chow ring, the degree complementing one. You don't have this on the permutohedron.
Question?
The point that's somehow we thought that it is natural to expect a nice geometric interpretation of this involution. Maybe something related to like a Hodge-star operator on the.
Is that the involution? That it sends the Bergman class to class of the dual?
Yeah.
So what if you try to do that on the permutohedral Chow ring? The numbers don't add up, right? Is that
The numbers don't add up, right?
Yeah, right.
The loopless condition is like
Yeah.
not good.
Yeah.
Yeah, somehow we thought that it must be the case that this has a nice geometric interpretation, whatever that might be. Never really could figure it out.
Is this even a Hopf algebra itself?
I don't know what that means.
For a single E?
Yeah, for a single E. Can you co-multiply inside the fixed ground set?
Why can't you do matroid union instead of matroid intersection?
Does that, yeah, so you take the dual of the product and you get it. Well, okay, maybe that's cheating though.
Yeah, so maybe there's something interesting that can be said, but
Do you multiply two Schubert matroids?
Yeah, right. So what are the structure constants when you multiply Schubert matroids?
Is it interesting?
I don't know. Anybody else know? I can multiply the co-rank 1 ones, I think. And then write down what you get. But I don't know in general.
I think it will either be, assuming you have the same chain, like it'll either be 0 or another Schubert, equal to another Schubert.
With multiplicity 1.
Yeah, if you multiply this gradient, that's.
Okay. Well, that's too easy for Schubert people.
wait, are you sure?
I think so. This is like multiplying simplicial generators where they have like a compatible chain. And then, I think that's what happens.
So sorry, how does the Schubert look in the more natural things in?
Products of simplicial generators,
Yeah.
where you take simplicity that are initial or final segments of your chain dependent convention.
All right, but I could have two monomials that have incompatible blacks.
I'm assuming they live in come from the same chain.
Even if they have incompatible, like, by the matroid intersection rule Graham said, it's either some matroid class or 0.
Yeah, but then I don't know what
Right.
I didn't understand the assumption or.
So when you define Schubert, you have like an ordering on the ground set.
Yeah,
Just when you choose the same ordering on the ground set.
why do you, does not make sense to not use it,
But then, yeah, it could.
but then it's difficult, no? I don't know.
Yeah, if you want to so these nested matroids form the additive basis. If you want to know how to multiply additive generators in general, yeah, that sounds like that could be pretty hard.
That could be, that's Schubert connection.
Yeah, I see, right, yeah. Yeah, right. So yeah, definitely if they're compatibly ordered, then we should all be able to work that out. But if they're nested, but in an unfriendly way to each other, then yeah, that's interesting. Maybe there's a combinatorial rule.
Sorry, I didn't get so is it just the product of the subsets corresponding here, or it's more complicated like this? How does
For an intersection.
no, but how does just the Schubert look like in the Chow ring?
It's the product of simple fusion, right? Monomial in simple fusion. Right?
The simplices I use are all initial segments, like this one will be, what will this one be like? You know, x brackets 4 squared, x brackets 6, x bracket 9 squared or something like that.
Yeah, right. Yep.
One shouldn't expect it to be positive in general, or no? You know, should it be positive?
Well, it's another matroid class by the,
No, yeah, well, in that case, but in the,
it's always, it's another intersection of two matroid classes, the matroid class or 0. So if you want it to be positive in the basis,
well, yes.
then I
that's the
guess
issue.
most of them aren't, unless you're, I don't know, right, what positivity do you want?
I mean, when you talk about structure constants for a ring, you usually do it with respect to a given basis.
Yeah, I don't think you're gonna get,
Positivity and that strong.
that sounds unlikely, yeah.
The question still makes sense. I understand.
It might, using these Möbius
Right?
coefficients,
But they also kind of don't make sense and you don't fix the big.
but you fix this basis, you get these Möbius coefficients, and I think they're a predictable sign.
Oh,
You know, they won't be positive, but I think they'll be somehow altered.
Well, thank you all for a fun seminar.
thank you.